these original graphs because they are needed to discuss our inverse function. So real quickly, what do the sketches look like? So a sine, remember, graphs the vertical change of a point as it spins around the unit circle. So it's the distance measured from the y-axis as I move around the circle. So at 0 degrees, I am hanging out right there at the origin. At 90 degrees, or pi over 2, my graph is up at 1. And then back at 180 or pi, I'm back to 0. And then at 270 or 3 pi over 2, I'm down to negative 1. And then back up at 2 pi. So remember, it looks like this. Smooth curve. Oops, didn't go through. No big deal. And then I'm having you graph it over 2 cycles, or 2 periods. So meaning we're going to negative 2 pi also. So we have the same thing just in reverse. And that would be your sine. Yes, something like that. A few of you guys had that. We're going to definitely need to know this shape. And the best way to remember how to graph sines and cosines, break them into quarters. Right? There's the first quarter, 1. Second quarter, back at 0. Third quarter, down at negative 1. Fourth, back at 0. All right, now cosine, though. Cosine measures the horizontal distance of this point as it spins around our unit circle. And so it would start at 0, you're going to be already up here at 1, because you're at 1, 0 coordinate-wise. And then at 90 degrees, x is your 0. And then at 180 or pi, I'm down at negative 1. Then back up to 0. And then back over there. So this is the one that starts up. Goes through its cycle. I'll do a similar thing going this way. Cosine. And then the tangent is the one we looked at yesterday. So tangent. This is that weird one. So remember there were some places where tangent doesn't exist? You remember what places those were? There you go. So we have pi over 2's and negative pi over 2's and 3 pi over 2's. So every pi over 2 plus another pi. So we have these, what are these guys called? Yeah, they're called asymptotes. So my graph is going to never hit those values. And then graphing-wise, what's happened? Well, at 0, I'm at 0. Say at 45 degrees. Tangent of 45, I'm at 1. Which means tangent of negative 45, I'm at negative 1. So this is the graph that kind of looks cubic in nature. Did this. Right, from over here with kind of, oops. No, I'm going to do that. It would do that. And on this side, something like that. So it would look like that between negative 2 pi. Now, look at all 3 of those graphs. Remember section, I don't remember the exact section. Chapter 4, we talked about things called inverse functions. Because anyone give me a little more refresher on what an inverse function is? X becomes y, very good. So equation-wise, switch x and y, solve for y. Graphically, what is it? What did we do graphically? We switched the x and y, just like we did when we rewrote the equation. Before I switched the x and y's, though, I had to determine whether it could even have an inverse. How did I do that? Horizontal line test. Vertical tells me whether I have a function. So horizontal line test tells me if I have an inverse. Will any of these pass the horizontal line test? Yes. It does? How many times am I hitting the curve? It's okay, you can kid. Yeah, so none of these will pass the horizontal line test unless I, what is it called when we say I only want to look at this portion of it? Well, I can talk about it as a period, but this is not talking about the period. I'm talking about when we said parabola. I don't want to see the whole thing. I only want to see this side of it or this side of it. What's that called? A domain restriction. So that is what we have to do to these graphs in order for Now, how do we restrict them? Well, we want to restrict them in such a way that I'm looking at its entire range, if I can. I'd like to include as much of the range as possible. I obviously don't want to look at the whole thing, because if I did, I wouldn't pass a horizontal line test. So, for example, on the sine curve, if I want to look at from a negative range value to a maximum range value, bless you, I would say, okay, let's chunk it out and look at this much of the curve. If I only looked from negative pi over 2 to positive pi over 2, that little portion right there would pass the horizontal line test. Let's go see what we would do for cosine. Where would I cut the cosine so that I can see the whole range? At pi and, I wouldn't go pi to negative pi, because that wouldn't pass horizontal line test. 0. I go from pi to 0. So we're going to cut this curve off, and we're going to look at it from there to there. So I have now something that passes horizontal line test. How about tangent? Where should we cut this? Well, I could go any place. You notice what I've been doing with the other ones? What have I tried to include? Well, I try to include a 0 if I could, right? We'll cut it off at 0 right there. But so why don't we do this for tangent? Why don't we slice it and only look at that portion right there. Now, restricting these domains, I'm able to pass horizontal line test, which means I can have an inverse. So that's what we're going to do today. We're going to take a look at the inverse functions. Now, these first 3 slides, I'm going to say don't bother trying to write it all down. There's a lot of information right here. I would go back and either print out the notes off the blackboard or go check out the YouTube later on. We have, up until this point, been working with our trig functions finding ratios. Y over x, y over r, x over r, r over x, r over y, x over y. Right? Yesterday we looked at reciprocal functions. Our cosecants, our secants, our cotangents, and tangents. We haven't done anything with regards to, hey, how do you find the angle? Well, that's what this does. This allows us to find an angle if I know a ratio of sides. So the inverse function is important for us to be able to do that. We're at chapter 8. We're getting down the road here. Again, we're coming up to the parts where we're going to be modeling trig functions, working with trig identities. Part of the modeling means I'm going to have to see if sometimes I get multiple answers for a certain ratio, meaning I can have more than one angle that produces a tangent value of 1. And that's what we need to be able to do. I haven't come up with that. Find that angle theta. All right, so, ready? There's a lot of little nuances in here, so we need to pay attention to what's going on. Generic function without any restrictions. F of x. Notice lowercase f, lowercase tan. F of x equals tan of x. That function, as we left it alone without a restriction, did not pass horizontal line test. We cut it off in this shaded region right here. And now we have a tangent function that passes horizontal line test. This shaded region, since we have restricted the domain of this thing, we're going to give the function a new name. Notice now capital F, capital T. That means I have the restricted function. Big difference between the little f, little t, big F, big T's. No restriction, domain restriction. The range and the domain values of these restricted functions are going to become important when it comes to finding the inverse. Remember that in a domain range situation with any function, when you wrote an inverse of a function, what did the domain become of the inverse function? Domain generically become the range. And the range of the original function becomes the domain. So that's what's going to happen here with this. So this domain of negative pi over 2 to pi over 2, when it becomes an inverse function, now becomes a negative pi over 2 for the range. And these all real ranges of the original function become all reals for the domain of the inverse. All right, so we do that. We restrict. We see the shaded area. Then we get to introduce ourselves to this new term, actually two new terms. We have the inverse tangent, which is where that little button on your calculator, tan -1, comes from. Also known as the arctangent of x. In fact, some of your calculators might even say arc, tan, arc, cosine, arc, sine. These are the inverse buttons. Again, these are allowing us to find the angle given a ratio. The reflections don't work any differently. If I took, for example, the y equal x line, kind of exaggerated, but here's my y equal x line for this tangent function. And if I took all the coordinates of the restricted graph, let's say that was almost negative pi over 2, -10, almost. And I switched them, it would become almost -10, almost negative pi over 2. Bam! Almost -10, almost negative pi over 2. And then I go back and I look at it again. All right, what about, let's see, this looks like there'd be negative, these are in radians here. Negative pi over 4, which is 45 degrees, would be about -1. That's about right there. That means -1, negative pi over 4 would show up. And I get something here. So I'm just switching my x's and y's from the original graph, just like we did before chapter 4, switching my x and y's, and I get this new function that is now my arctangent function or my inverse function. Notice again, capital F, capital T. This is the new notation that we must get used to. Big letters. Telling me I have an inverse, which means I'm looking now for the angle theta, or in this case you'll notice it's an x, right? So x, theta, whatever is inside of here, that's my angle. And there are my domains switching, right? My range becomes domain. My domain became range. And this is the one that we are really interested in. Because this tells me my possible answers for inverses of tangents. When I take an inverse of a tangent function, I have to get an answer that is between negative pi over 2 and pi over 2. If it's outside of that world, it's not part of the inverse. It's got to remain in that world. So from negative 90 to 90, when I do inverse stuff for tangents, I'm going to get my theta. And it's going to be the case for sines and cosines. It's going to be the same thing. So here's that switch and solve thing that we talked about, and how we write one equation into an inverse equation. So we had the original functions, tan x equal y. We switch the x's and y's. Now they become tan y equal x's. And remember what these parts mean. That is an angle. This is a ratio of sides. So now what happens is, that's now a ratio, and this is now an angle. So when I go and I solve for the inverse tan, I am now looking for theta. No longer looking for ratios. This is the part that's confusing for some people. Because there's two equations that look a lot alike. There's this equation, and then there's this equation. Main difference. One of them has a -1 power at the end of it. That's your inverse function. In this equation, ratio, angle. In this equation, angle, ratio. That's the thing we got to get stuck in the head, is that when I have an inverse of something given to me, I've been given the y over the r, the x over the r, the y over the x, whatever it is. I've been given the ratio, and I'm trying to find the angle that produces that. Somebody in third period was confused about that. Came back, asked, real quick to clear it up, but this is kind of what I showed her. Just think, that's my ratio, that's my angle, switch it. And now I get the opposite. Does that make sense? Yes, no, maybe. Okay. If I originally solved for a ratio, and I'm writing an inverse now and switching to the other thing and solving for the angle instead. All right, so that's my tangent and all the details that go along with the tangent. The way the curve looks, the restricted part of it. Now, the next two slides are just going to be what happens with the sines, what happens with the cosines. We're going to go through these pretty quick, and then we'll get into some example problems. Sine, little g, g of x equals sine of x without a restriction. We know it just keeps going on, domain, negative infinity to positive infinity, but we don't want to see that, so we restrict, and we only see this shaded area now for sine between negative pi over 2 and pi over 2. Allows us to pass horizontal line test. Now my function becomes big G, big sine. Domain stated, range stated. Notice the range though, not like the tangent function. Tangent has infinite range. Domain on, or range on sines and cosines have to be between negative 1 and 1. So those guys are going to now flop when we write the inverse function. So here comes the inverse function. Now it's big G, big sine with negative 1 powers, telling me I'm taking the arc sine or the inverse sine. Taking my y over x, reflecting my points, I get this new graph right here. That's what the arc sine graph looks like. And then notice that it too has the same range values as the tangent function. Meaning, when I find inverse sine equations, I'm going to get negative 90 to 90 or negative pi over 2 to pi over 2 are my only possibilities. If I get something else, then, well, I won't get something. Those are the only ones I can have. What does the cosine guy look like? Little h, little cosine, restricted domain, shaded area. This is different. Notice I'm not on the left-hand side of the y-axis. I'm now strictly in what would be quadrant 1 and 2, from 0 to pi. And I see there I can pass horizontal line test with that. So difference in the sense that I'm not going between negative 90 and 90. So when I write the inverse of this, big H, big cosine, here's my graph reflected. This is the only one where I can go all the way out to 180 degrees. So you're going to find when we do some example here in just a second, that when you do inverse cosines, you'll get answers between 0 and 180. When you do inverse sines and inverse tangents, you get answers between negative 90 and 90. Okay, so there I am, throwing it all at you in a matter of minutes. What these things look like, where they come from. Remember, the big emphasis here is what I've underlined with the range. That is our objective with this inverse stuff. We're trying to find the angles that produce this ratio psi. Okay, before we roll on to some example problems, what questions are there? Nada? Okay, so let's try some stuff. Find the inverse tan of 5 with calculator and degrees of range. So let's just remind ourselves what it is we're looking for. I'm asking you to do this. Where this x value, which is my what? What is this again? My ratio is 5. My ratio is 5. Does a ratio have any units attached with it at all? Nope, no units. So if I'm supposed to find my answer in both degrees and radians, what do you think I need to do with my calculator? Switch them. So let's find it in degrees first. So the calculator is going to tell you, in degrees, if I have a ratio of 5, meaning I had a y of 5 and an x of what? 1. A y of 5 and an x of 1. What would be the angle that helps me create that? That's what this is doing. Little visual here. I've got a y of 5 and an x of 1. I'm wanting to know, what is that? What angle produces that? What is it? 78.69? Okay, does this angle fit within the range of our inverse tangent? Yes, it does. What's our range for our inverse tangent? Negative 90 to 90. This fits within the range. This is okay. If it doesn't fit in the range, it's not okay. It doesn't work. We can't use it. Now, what we're eventually going to be doing with this, chapter 8, next section, is we're going to find that there are actually two answers that produce a ratio value of 5. Where would the other quadrant be that does this? Quadrant 3. Why quadrant 3? Why? What's the acronym? All support the covers. That's right. That's right. So all support the cover. This is the reason why. Tangent is positive here. Tangent is positive here. So I will eventually be able to say there's another answer. There's another angle that also produces a tangent of 5. Does anyone want to care what that answer is? I'm going to guess what it might be. Add 180 to it. Why? You know. Do you remember my rules for thetas and alphas and my 4 quadrants? What are my rules for theta? We're kind of getting ahead of ourselves. Alpha is theta. Here. What is alpha here? 180 minus theta. Alpha here is theta minus 180. Alpha here is 360 minus theta. Remember, alpha is your referencing. So in this case, when I do this, is that a referencing? Is this a referencing? Because it's in quadrant 1, it has to be. This is a reference angle. So this is the same thing as my alpha, which means if I wanted to, we're not doing that here because we're just trying to find the inverse worlds. If I wanted to find the other angle that produces a tan 5 ratio, I would say 180 plus 78.69, and I'd have 258.69. There's my other angle that produces it. But we're just going to concentrate on finding the angles that fit within our range values for our inverse functions. Right? All right, what was it in radians then? 1.37 radians would be the equivalent. Okay? All right. So there will be parts of this stuff that will be on the no calculator portion of your fun times. That obviously wouldn't, because we don't know the ratio of 5. It's not one of my special right triangles. If it's only my special right triangle stuff, that will be on the no calculator portion. All right, let's roll on here. Stop me. You guys have questions? Without a calculator, let's find the expression. And again, remember, not each of these. Some of these, if they're on quadrantal angles, you may not have two answers. If I'm not on a quadrantal angle, though, which A and C, those are both not on quadrantals, I could have two answers to this, but we are, again, only looking for the answers that fit within our restriction of our inverse functions. So maybe what you want to do, just to remind yourself, is once you know what inverse function you're talking about, maybe then just give yourself a little reminder of what my range is supposed to be. My answer should be between negative pi over 2 and pi over 2 for this one. What should my range be for this one over here, son? You can go back and peek. What was our restriction on our range? It's the same thing, wasn't it? And what about our cosine? Yeah, 0 to what? Yeah. Alright, so maybe we just put those there and remind ourselves. That's my answer I'm looking for. Stuff that fits within those range. Although I could find two answers because eventually we're going to be doing that. Alright, so without a calculator, how do we do this? Are you kidding me? No, I'm not kidding you. once again, this is my y over x ratio. So I draw a little picture to tell me where I'm at. I'm supposed to be somewhere between negative 90 and positive 90, which means I'm in quadrants 1 or 3. What do I have to be in if my ratio is positive root 3? I got to be in quadrant 1. All right, so here's my triangle then. If this is supposed to be a y over x, then that means my y is a root 3, my x is a 1. No number done underneath there. So my y is a root 3, my x is a 1. This is the theta that we are finding. There it is right there. What is that angle? Well, hopefully you're going to recognize the sides of 1 in root 3, and you're going to know what triangle that comes from. 30, 60, 90. Very good. What is the angle across from a root 3 side? 60. There's my answer. Without a calculator, we found that the angle across from a root 3 side has to be 60 degrees. Now test it. If you're not sure if this is right, put your calculator in degree mode. Go tan of 60. You're going to get a decimal value. Take root 3. See if you get the same decimal value. They will be the same thing. That's my answer. It's not that bad, is it? Is that bad? Alright, so there's my angle. It fits within my range between negative 90 and 90, so we're good. That's Alright, B, what do I do there? Walk me through it. Don't all volunteer at the same time. Oh, there you go, Cameron. So first of all, Cameron, tell me what my ratio. What is this ratio right now? Yeah, that's true. What is the sine ratio? Y over.
It's y over r.
Okay, good. So my sine ratio right now is y over r, which is equal to negative 1. All right. Where am I?
You're in quadrant 4.
I'm in quadrant 4?
Yes.
Are you sure about that?
Yeah.
If I'm in quadrant 4, that means I'm over here somewhere.
Yes.
Where is the only place where sine is negative 1? The only place in the world where sine exists. 3. No, not quadrant 3. On the line, which one? The vertical. Why is it on the vertical? Why is this the place where sine is equal to negative 1? What does sine measure? Y. And if the y over r is negative 1, that must mean it's a negative 1 over a 1. And if that's true, that the y and the r are the same thing, this is the only place that that point can exist. And so on our quadrantal angles, this is why I was telling you guys for the quadrant, for the unit circle, you know this stuff. You need to know this stuff. Quadrantal angles are the tricky ones. Those are sine and cosine values right there. Every one of those x's is a cosine value. Every one of those y's is a sine value. So the only place the sine is negative 1 is right there. All right, so if that's the case, what's the angle that that thing is hanging out at? What? That's not angle 0. That's 270. That angle is 270. From here to there is 270. So the answer to this is only one answer. The theta would equal 270. However, does that fit within our range? So how do I need to write it? Not 90. Negative 90. Even though they're the same thing, they are the same thing. And this is true that sine of 270 is negative 1. If we're just writing it to fit within our range for our inverse sine function, I got to use negative. Can't use 270. Yes?
So how does that
the range is between, they should both be or equal to something. The range is in between negative 90 and positive 90. If we go back to that curve for our inverse sine. Yeah, I forgot to put or equal 2 bars underneath there. My fault. Sorry about that. So that's why it's going to be negative. So those quadrantals, we got to make sure we're understanding quadrantal stuff. 90s, 180s, 270s, 360s, those are special conditions I have to be careful of. All right. So this next one, we got this little asterisk saying, be careful with the range values on this one. So cosine is that one. It's the only one that's unique because it goes from 0 to 180 for its range values, not from negative 90 to 90. So let's find out where we are here. So where do I draw my triangle? Quadrant 2. Very good. How did you know that, Parker? Okay, it's negative cosine, and so cosine is only negative in quadrants 2 and 3. The reason I can't be in quadrant 3 though is because quadrant 3 angles don't fit within my range. So I'm going to be in quadrant 2. So my triangle is here. Okay, let's put the parts of the triangle together. What is the root 3 part of my triangle? It's the x part, so it's down here. It's negative, because I'm on the left-hand side of the origin. What's the 2 part of this? That's my r. All right, there we go. So we have our parts in here now. So there's my triangle. And again, I recognize those pieces to be a part of a what triangle? 30, 60, 90. And what is the angle that is across from the root 3? 60. So there's my 60, which means this one is my 30. My 30-degree angle right there. All right, so the answer to the question, what is this angle? What is that? 150. So here's where the reference angles are going to come in handy, and here's where you got to be careful with cosine. Everyone get your calculator out and put in cosine of negative 3 over 2 and tell me what the answer is. Be careful how you put it in there. Cosine negative root 3 divided by 2. Make sure you're in degree mode too. 9998. Are you in degree mode?
Yeah.
Okay, when you put it in, did you do inverse cosine? You got to do inverse cosine. Don't do cosine. Inverse cosine of. Okay, good. We get 150. So if I had done this with sine or tangent, I'm going to get a number that is absolute value-wise would be a reference angle. This is not a reference angle. Why? Why is 150 not a reference angle? It's bigger than 90 degrees. But if I know that theta is 150, can I find alpha? Yeah, and that's what we just did, right? We said alpha is equal to 30. How did we get that? Well, we knew that I had 180 minus this angle, or we knew because of my triangle that that was 30. But if I had known that theta was 150, I could very easily have found that the alpha is 30. So cosines you got to be careful with because they will not help you find all of the time your reference angle unless you're hanging out in quadrant 1. If it's a cosine inverse of a negative value, you're going to find something between 90 and 180 as your theta. And it's not wrong. Because does this fit within the domain or the range restriction of a cosine function? It does. It is in between 0 and 180, so that's true. Looking ahead again, chapter 8, there's another answer, though, of what would be equivalent to a root 3 over 2 negative value for a cosine. What would the other angle be? That's one of them. Well, what's the other angle that produces the same ratio? 210. It's 210, and it's 210 because it would have been down at quadrant 3. My other triangle would have been here. It has the same reference angle. And in quadrant 3, remember this is our rule. So if I knew what my reference angle was and I wanted to find theta, I would just do that. 30 plus 180, 210. That would be another angle called theta 2. That would give me the same answer as an inverse cosine of negative 3 root 2, or a cosine of 150. Cosine of 150, cosine of 210, both produce that ratio. Again, we're just looking for the ones that right now fit within the range of our inverse sine, inverse cosine, inverse cosine. Next chapter, we will be talking about both of those answers. You have to give me both of them. All right. Anything? Questions? All righty. How about this guy? Find the approximate and the exact. The approximate's easy. Let's see if you guys can set this thing up. Is that what you got? Oh. So how did he get that? I was excited. Okay, watch this now. Remember, right now, this is set up like that. It's saying cosecant of theta. What is our theta? Inverse cosine of negative. Theta is equal to this giant mess. So, if I can find that, get that angle, plug that angle in here, and then take the cosecant of it, I've got my answer. So, go ahead, plug in the calculator here. What is the inverse cosine of negative 0.4? What do we get? Make it now. You know, I don't care what boat you're in, degree or radian.
1.98.
Yeah, radians 1.98. So theta radians 1.98. Anyone get theta degrees? Okay. Are we good? Is that right? Okay, so if this is my angle, or my radian or my degree angle, then simply finding my cosecant of that thing would mean just saying, all right, if I'm in radians, I'm going to do the cosecant of 1.98, get an answer. Or if I'm in degrees, I'm going to do cosecant of 113.57. Wait, before we go on with the 113.57 or the 1.98, do both of those fit within the range of an inverse cosine? Yes? No? What's the range of inverse cosine, folks? 0 to pi. What's the range of inverse sine and tangent? Negative pi over 2 to pi over 2. All right, we got to get that locked in and loaded. All right, so anyway, either of these, whether degree or radian, would give me the 1.09. That's my answer. So that's the approximate answer. That's not the exact answer. So how do we go about finding the exact answer for this thing? Are there questions on that? Where that came from? Yes. So cosecants, well, cosecants we're not worried about. But for cosine inverses, for inverse cosines, the range is between 0 and pi. That's all you need to know, because all that tells me is when I get an answer of theta, it better fit within here. And if it's not, we got to make it fit. No, because we're not dealing with the inverse cosecant. Yeah. All right, so how do we find the exact one? That's a good question. Here's the hint. Whoops, there it went. For the exact ones, we need to convert this decimal into an equivalent fraction. So how do we make 0.4 become an equivalent fraction? Everyone like talks at the same time. So what? Say what? Negative 4 over 10. Can I reduce it? Negative 2 over 5. So how do you make a decimal become an equivalent fraction? Well, first of all, negative we won't worry about right now. 0.4. Right now I'm in the 10th place. We're backing up a little bit. Way back. So if I want to be an equivalent fraction, I'm going to do something over 10. Well, whatever this is, goes right there. Don't worry about the decimal anymore. So 4 over 10 becomes 2 over 5. So that's what I'm going to use now. And I'm going to solve for the cosecant of the inverse cosine of 2 negative 2/5. This is going to set up the same exact way, but now I don't need the calculator. And this is actually easier. I think it's easier to do it this way than it is to do the calculator. Because this inverse cosine part creates a triangle. And from that triangle, I find the theta. And once I know the theta, I can find my cosecant. So let's see how this all pans out. Let's take this and create our triangle out of it. Where am I for an inverse cosine to be a negative 2 over 5 ratio? Second quadrant. Very good. I'm in quadrant 2. What are the parts of my triangle? Whoa. Negative 2/5 is x. Want to change that? Negative 2 is x. And 5 is r. All right. Now, I could just stop here and realize that's my angle theta that produces that triangle. But the thing is, with cosecants, what are my ratios for cosecants? R over y. So a cosecant is an r over a y. We don't have a y. Can we find it? Yeah, we can find it. What is it? Pythagorean theorem. So I have 5 squared minus negative 2 squared. So 25 minus 4 gives me 21, which means this side of the triangle is a square root of 21. Now I have everything I need to be able to solve for the cosecant. So remembering that all of this stuff right here is equivalent to what? What is that? That's theta. This stuff right here is theta. So I'm saying, let's find the cosecant of theta. Well, here's our theta. There's our theta right there. And if cosecant is supposed to be an r over a y, look at our theta and tell me what the r and the y is. What's the r and y that make that? 5 over square root of 21. Can I leave an answer like that? No, we got to rationalize it. So I got to multiply both sides by square root, top and bottom. So I get 5 root 21 over 21. There is the exact answer for the cosecant of the inverse cosine of negative 2. If you were to punch that in the calculator, 5 times square root of 21, take that answer, divide by 21, you're going to get, guess what? 1.09. Yeah.
What measurement is that?
Great question. Ratios, are they any measurement? No. They can be unitless. Yeah. I could physically have like a measurement on these triangles. I would talk about feet or miles or whatever. We're just looking for the ratio. We don't care about the units. So I don't know. I kind of think that's an easier way to do it. You don't have to actually use the calculator. Just building your triangle using Pythagorean theorem to find a missing part, understanding what ratio you need based on the trig function you've been given, and then. You guys agree with me? Probably not. You guys are disagreeable. Disagreeable? Okay, I might have just talked at the door. All right, your turn to try. Unless there are any last minute questions, they're going to give you some nice round. Any last minute Precalculus? Okay, so your turn.